In the context of general relativity, this research paper proposes a novel model for the gravitational collapse of dark matter in the presence of quintessence or phantom-like scalar fields, up to the point of virialization. The authors consider a spherical patch undergoing gravitational collapse, similar to the top-hat collapse method, and examine the effects of dark energy on the collapse process. Their findings indicate that the dark energy sector maintains a profile similar to the background expanding Friedmann-Lemaitre-Robertson-Walker universe, while the dark matter sector collapses. However, a closed FLRW isolated collapsing patch is not viable in general relativity, and instead, an external generalized Vaidya spacetime must be matched with the internal spherical patch guided by the FLRW metric. This setup reveals that almost all collapses are accompanied by a flux of matter and radiation in the generalized Vaidya spacetime. Furthermore, some spherical regions of the universe are found to expand eternally, producing void-like structures. The fate of a spherical region, whether it collapses or expands, depends on the initial values of the system and model parameters. The authors suggest that the emission of radiation from collapsing structures could serve as an observational signature of their proposal. They also highlight the importance of dark matter in structure formation, assuming it to be a fluid with zero pressure that follows the gravitational potential produced by a marginally denser region. The paper discusses the limitations of traditional lambda-CDM models and the introduction of dynamical dark energy models based on scalar fields, such as quintessence and phantom-like scalar fields. The authors emphasize that their model provides a more nuanced understanding of structure formation, particularly in the context of dark energy and dark matter interactions. The study explores the gravitational collapse process in a two-component universe, where dark matter and a scalar field act as sources of dynamic dark energy. It addresses the limitations of previous works by adopting a more relativistic approach, incorporating the emission of radiation from the boundary of the collapsing region. This is achieved by matching the internal FLRW patch with a generalized Vaidya spacetime before the internal spacetime closes. The model predicts the effect of gravitational collapse on the dark energy sector, which reacts by transforming locally into radiation. The study also discusses the virialization process and the existence of large-scale structures, acknowledging the need for a phenomenological approach beyond the relativistic formalism to explain the formation of singularities and the existence of large-scale gravitationally bound objects. In the context of a two-component universe, the semi-Newtonian theory of virialization is explored, with a focus on the dark matter and dark energy sectors. The total gravitational potential of the overdense region is defined, incorporating both dark matter and dark energy contributions. This potential, described by equation 1, is derived by integrating over the volume of the spherical overdense region. 4 distinct scenarios are presented for the two-fluid system, differing in the role of dark energy in the gravitational potential. These scenarios include neglecting dark energy, assuming a homogeneous dark energy distribution, allowing dark energy to cluster but not virialize, and finally, permitting both clustering and virialization of dark energy with dark matter. The effects of dark energy on the virialization process are illustrated in Figure 1, which depicts the variation of eta with Q for each scenario. This graphical representation highlights the significant impact of dark energy on the virialization process, demonstrating the need for a nuanced understanding of its role in shaping the large-scale structure of the universe. In the context of dark energy, the dynamics of spherical overdense regions are crucial for understanding the virialization process. The total gravitational potential energy of such a region becomes the total energy at the turnaround radius. This total energy, calculated using the equation ET, T equals T max equals VT equals 1/2 ZV max rho dm phi dm dV equals -3 m2/5 Rmax, is a key parameter in determining the virialization time. At this point, the total kinetic energy of the overdense region equals the negative of the total potential energy. The introduction of dark energy into these calculations significantly impacts the virialization process, particularly in homogeneous dark energy scenarios. The total potential energy of the overdense region must be modified to include the energy density and negative pressure of dark energy. This results in a new equation for the total potential energy, which depends on the equation of state of dark energy and the ratio of dark energy to dark matter densities. The virialization condition is then used to derive a cubic equation for the parameter eta, which describes the virialization process. Solutions to this equation are discussed for different dark energy models, including the cosmological constant model. The presence of dark energy affects the value of eta, making it less than 0.5 for models involving the cosmological constant. However, a problem arises in homogeneous dark energy models due to the changing dark energy density. This issue is resolved in clustered dark energy models, where the dark energy density is not uniform throughout the universe. The implications of these findings on our understanding of dark energy and its role in the universe's evolution are profound, highlighting the need for further research into these complex phenomena. The authors derived two scenarios for the total gravitational potential energy of spherical overdense regions, contingent upon dark energy's ability to cluster and virialize within these regions. In the first scenario, the total potential energy is governed by equation 9, which relates the energy density contrast eta to the dark energy equation of state omega and the radius of the overdense region Q. Alternatively, the second scenario yields equation 10, leading to equation 11 for eta. Figure 1 illustrates the deviation of eta from 0.5 for varying Q values, depending on dark energy's clustering and virialization capabilities. When dark energy can cluster and virialize, eta exceeds 0.5, as shown by the brown line. Conversely, when dark energy can cluster but not virialize, eta falls below 0.5, represented by the green line. The blue curve depicts the case where dark energy is modeled as a cosmological constant. To describe the cosmological scenario where dark energy is homogeneous and influences the collapsing dynamics of overdense dark matter regions, the authors introduce a two-fluid model. This model represents the energy-momentum tensor as the sum of the energy-momentum tensors of dust-like matter and a scalar field. A closed FLRW spacetime is employed to model the collapsing fluid, assumed to be homogeneous and spherically symmetric. The scale factor of the overdense region, denoted by A, T, is set to 1 at t equals 0, with a continual gravitational collapse leading to a singularity when A, T, reaches 0 at a comoving time ts. The background is modeled using a flat FLRW spacetime, with the dynamics described by a two-fluid model. Additionally, an external generalized Vaidya spacetime is considered to describe matter flux through the boundary of the overdense region, although this is not treated as a background spacetime. The research paper delves into the collapse of overdense regions in the universe, with a specific focus on the influence of quintessence-like and phantom-like scalar fields. A two-step approach is employed, first utilizing the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric to describe the internal dynamics of the overdense region, and then employing the generalized Vaidya spacetime for the external dynamics. The paper presents figures illustrating the allowed parameter spaces for V0 and ρm0, where the overdense region collapses after reaching its maximum physical radius. This collapse is examined under the presence of both quintessence-like and phantom-like scalar fields. To match the internal and external spacetimes at the time-like hypersurface sigma, the induced metric and extrinsic curvature from both sides must be equal. This leads to equations 19 and 20, which represent the necessary conditions for smooth matching of the spacetimes. The four-velocity and spacelike normal for the comoving shell sigma are calculated from the side V-, while the expressions for U alpha plus and N alpha plus are derived from the side V+. These expressions are crucial in determining the azimuthal components of the extrinsic curvature tensor, which will be used to analyze the collapse dynamics in the subsequent sections of the paper. The research paper presents a detailed analysis of the scalar potential V, phi, equals V0 e caret, elf, for a quintessence field in the context of collapsing spacetime. It focuses on the variation of different variables with varying V0, as depicted in Figure 4. The extrinsic curvature tensors kth plus and kth are calculated and equated, leading to an expression for the Misner-Sharp mass f, t, sin psi b, of the internal collapsing spacetime. This mass is a function of time only, representing the internal homogeneous two-fluid system. The paper also discusses the non-zero pressure at the boundary of the system, generated by the presence of a scalar field. This pressure is responsible for the non-zero matter flux through the boundary, with inward flux for expanding scenarios and outward flux for collapsing scenarios. The expression for pressure, given by P equals F, R squared, highlights the importance of the scalar field in generating this pressure. The study examines the relationship between the flux of matter at the boundary and the scale factor, as well as the Misner-Sharp mass of the collapsing spacetime. The time dependence of F implies that the pressure is non-zero internally, and the scalar field plays a crucial role in this process. The authors delve into the dynamics of a two-fluid system, consisting of a scalar field and matter, with minimal coupling between them. This system is explored within the framework of a generalized Vaidya spacetime. The scalar field is described by a quintessence potential, V, phi, equals V0 e caret, elf, where lambda is a parameter that influences the system's behavior. Figure 5 illustrates the variation of different variables with respect to the parameter lambda. It shows the evolution of the scalar field, A, the angular frequency, OFF, the energy density ratio, ARF, ARF, and the angular frequency of the scalar field, omega t, as functions of time. Notably, the matter field part of the system does not leak out of the boundary, whereas the scalar field continuously leaks out throughout the dynamics of the overdense region. This is due to the matter having zero pressure at the boundary, whereas the scalar field has a non-zero pressure. The energy-momentum tensors for the internal and external spacetimes are written as T-Mn and T-Mn, respectively. These tensors are expressed in terms of the energy density, pressure, and velocity of the matter and scalar field. The energy density, E, and pressure, P, of the external spacetime are written in terms of the mass, m, and velocity, v, of the null dust and perfect fluid. The null vectors, L mu and K mu, satisfy the condition L mu K mu equals 1. The existence of non-zero pressure at the boundary cedes the components of the energy-momentum tensor of the external generalized Vaidya spacetime. In the next section, the authors will solve Einstein's equations for the internal spacetime, considering the scalar field to be either a quintessence field or a phantom field. The matter density, ρm, varies as 1, a cubed, making the matter part evolve like a closed dust ball. The internal density of the scalar field remains almost constant throughout the evolution, implying a non-zero flux of the scalar field through the boundary. The initial matter density is considered to be 10^310 to the power of 4 times greater than the initial density of the scalar field, allowing the use of the virialization technique to understand the virialization process of the two-fluid system. In the context of gravitational collapse, this section delves into solutions involving quintessence and phantom-like scalar fields. The effective density and pressure of the resultant fluid are derived using Einstein's equation for the FLRW spacetime, emphasizing the significance of the scalar field potential V, phi, curvature parameter K, and time derivatives in these expressions. The conservation equations for both the scalar field and dust-like matter are examined, revealing that the energy density of matter decreases with the scale factor A as ρm proportional 1, A3. The dynamics of the scalar field are also explored, including the expression for ARF plus P phi and the second-order differential equation governing the collapse. A specific potential for the scalar field, V, phi, equals V0 e minus elf, is chosen due to its association with quintessence-like fields. This setup provides a framework for understanding the intricate interplay between matter and scalar fields during gravitational collapse, offering insights into the complex processes involved in such cosmic events. The figure on page 10 illustrates the variation of different variables with time, considering a scalar potential V, phi, equals V0 e minus elf for the quintessence field. This model assumes ρm equals ρm0 and K equals 1. The equation of motion derived from the action is -4 volts 0 e minus lphph, A3 plus 9 phi, A plus V0 e minus lphph3, A5 2 plus ρm0 phi 3, A2 4 minus phi 3, A3 plus 3 lambda of 2 volts 0 e minus elf minus 5 ρm0 phi, A2 minus ρm0 a phi, A plus 3 A2 phi, A minus V0 E minus elf A4 phi. A minus lambda V0 E minus LPHPH2. A4 2 equals 0. This equation encapsulates the dynamics of the system under the specified potential. The plots demonstrate the temporal evolution of various quantities such as A, OFF, ARF, ARF, and omega t for two different values of ρ m0, namely 5 and 6. The top panels show the variation of A with time, indicating the scale factor's evolution over time for different initial matter densities. The bottom left panel illustrates the variation of OFF with time, representing the virialization state of the quintessence field. The bottom right panel presents the variation of ARF, ARF with time, providing insight into the relative energy densities of the quintessence field and matter. Finally, the bottom panel depicts the variation of omega t with time, showcasing the evolution of the equation of state parameter for the total fluid. This figure provides a comprehensive overview of the quintessence model's dynamics under the given potential, shedding light on its implications for understanding the universe's expansion and the role of dark energy. The authors present a set of differential equations that govern the dynamics of a scalar field phi, A, and the scale factor A, T, in an overdense region. Specifically, they derive equations 44 and 45 for the phantom-like scalar field, which has negative kinetic energy, and equations 43 and 46 for the quintessence-like scalar field. These second-order differential equations require two initial conditions, phi A equals 1 and phi A equals 1, to be solved. The authors choose specific values for these initial conditions and explore the parameter space of V0, ρ m0, and lambda to compare their model with the standard top-hat collapse model. They identify scenarios where the overdense region undergoes an initial expansion phase followed by collapse, and show the parameter space of V0 and ρ m0 that allows for this dynamics in the presence of quintessence-like and phantom-like scalar fields, respectively. They find that certain values of these parameters lead to an ever-expanding dynamics, while others result in a spacetime singularity. To stabilize the system, the authors invoke the Newtonian virialization technique, which is commonly used in the standard top-hat collapse model. However, they note that the presence of two fluids, one of which is non-dust, may affect the virialization radius, which may not be equal to half of the maximum physical radius. The authors plan to use equation 7 to calculate the virialization radius of the overdense region, assuming the scalar field behaves like homogeneous dark energy. The two-fluid model is employed to simulate a homogeneous dark energy scenario, where the scalar field acts as dark energy and dust-like matter represents dark matter. By altering the values of V0, ρ m0, and lambda, the dynamics of the overdense region can be varied. Figure 7 demonstrates the variation of different variables with V0 for the scalar potential V, phi, equals V0 E minus elf. This figure illustrates the evolution of dynamical quantities such as A, OFF, ARF, ARF, and omega t with time for different V0 values. The density ratio ARF, ARF increases with comoving time and stays close to 1, indicating that the quintessence-like scalar field behaves like homogeneous dark energy. The model considers suitable small values of V0 and ρ m0 to achieve this behavior. In the context of an inhomogeneous universe, the scalar potential's variation with respect to different variables is crucial in understanding the behavior of the scalar field. Within the overdense region, the scalar field exhibits distinct characteristics, which are influenced by the scalar potential's spatial dependence. Notably, the scalar field's amplitude decreases as the scalar potential increases, indicating a suppression of the scalar field inside the overdense region. The evolution of the scale factor, scalar field density, and total equation of state are intricately linked. The scale factor's growth is slowed down due to the presence of the quintessence-like scalar field, which contributes to the total equation of state. The scalar field density, on the other hand, decreases as the scale factor increases, implying a dilution of the scalar field with the expansion of the universe. Comparison with the homogeneous dark energy model reveals similarities in the scalar field's behavior, particularly in the high redshift regime. However, a key distinction lies in the time intervals for virialization. The presence of the quintessence-like scalar field delays virialization, resulting in longer time intervals compared to the homogeneous dark energy model. This disparity has significant implications for the formation and evolution of structures in the universe. By examining the variation of the scalar potential and its impact on the scalar field's behavior, this study provides novel insights into the inhomogeneous universe, highlighting the importance of considering the quintessence-like scalar field in cosmological models. The figures depicted in Figure 9 illustrate the variation of different variables with respect to time for different values of ρm0 in the top-hat collapse model, with the scalar potential v, phi, equals v0 e-elf, mimicking a phantom field. Specifically, Figure 9a and 9b display the evolution of the scale factor A with time for ρm0 equals 5 and ρm0 equals 6, respectively. Figure 9c shows the variation of OFF with time for ρm0 equals 5 and ρm0 equals 10, whereas Figure 9d illustrates the variation of ARF with time for the same ρm0 values. Lastly, Figure 9e displays the variation of omega t with time for ρm0 equals 5 and ρm0 equals 10. The analysis of these plots reveals that the model of a two-fluid system, comprising pressureless matter and a quintessence-like scalar field, closely resembles the homogeneous dark energy model. This similarity is also observed in Figure 6, where ρm0 is varied. Furthermore, Figures 7, 8, and 9 demonstrate the dynamics of A, OFF, ARF, and omega t for various values of v0, lambda, and ρm0 in the presence of a phantom-like scalar field. The results show that ARF approaches unity and OFF approaches 1, indicating that the phantom-like scalar field in the model behaves akin to homogeneous dark energy. Thus far, the discussion has focused on top-hat-like collapse in the presence of quintessence or phantom-like scalar fields. Gravitational dynamics in a two-component system consisting of pressureless matter and a scalar field with a quintessence or phantom-like potential are examined. The collapse and expansion of spherical overdense patches in the universe are investigated, depending on the potential parameter and initial matter density. The authors find that certain regions will collapse, leading to gravitational collapse, while others will expand eternally, producing voids. This dichotomy is attributed to the interplay between the scalar field's potential and the initial matter density. The model predicts that collapsing regions will emit Vaidya radiation, a unique feature of this framework. The study's results have significant implications for our understanding of structure formation and the large-scale distribution of matter in the universe. The model's predictions, including the emergence of voids and the radiation signature from collapsing regions, provide a novel avenue for observational comparisons. Future work will focus on confronting the model's predictions with observational data, enabling a more comprehensive understanding of the gravitational dynamics in these two-component systems. The authors acknowledge that the simplifying assumptions of spherical symmetry and neglect of dark energy perturbations may limit the model's applicability, and future refinements will aim to address these limitations. The research paper acknowledges the support provided by the Atlantic Association for Research in the Mathematical Sciences, AARMS, for funding the work. It concludes with a comprehensive list of references.